Okay, here we come to the next simulation I want to show you. I showed you in the last slide something about meshes. You know already how to do meshes, but one thing I have not explained you already. You have different types of numerical simulations for fluid flows. You can do simulations on meshes. That's what we did was on the CFX, but you can also do simulation without meshes in another mathematical system, the so-called Lagrangian system. And the Lagrangian system is completely different if you compare it to the Eulerian system. So there's always this conflict between Eulerian simulation and Lagrangian simulation. And what is Lagrangian simulation? Lagrangian simulation, if you do a Lagrangian simulation, you don't have a mesh at all. Sounds funny, but you do not use fixed coordinates. You use the coordinate of single particles. So the Lagrangian simulation is really good if you do simulations for particle flows or particle clouds. For example, I did a lot of the simulation for oil or gasoline droplets or for diesel droplets. This is for example a simulation of a direct injection gasoline system. It's a gasoline, I think it was a General Motors nozzle, because General Motors has always symmetrical holes. I was interested in how the gasoline spray will be positioned inside the cylinder. It is always a problem if the gasoline spray hits the sparkler, or if the gasoline hits the valve or the walls of the cylinder, then you will get problems with emissions or problems with fuel consumption. If you hit the cylinder wall, the fuel will not be used for combustion. So I decided to make spray simulations with the Lagrangian system, and I painted every droplet or every particle after the hole I injected it with. And so I got different colors, and here at the beginning you can you see for every single plum of spray a different color. But if you look at the last fourth time step, you see that you get a mixing of the cloud, the particle cloud. Okay, of course it's better if you show this with a movie. And here I compare both systems. We have the Eulerian system where we have a fixed coordinate system, a fixed mesh. The mesh is the coordinate system, and the mesh is the same. Yeah? And the other principle is the so-called Lagrangian principle. Here we don't have a mesh, but we have the position of every single particle, and then you make the simulation, you have changing coordinates for every particle. And let me tell you, this is more complex system, this more complex simulation, and I can explain you why. If we have a fixed coordinate system, we can define the space we need in the memory and the RAM. We can define the addresses really good. We can order them before we solve the equations. But if we have a not fixed coordinate system, if we have changing coordinates, you always have to change the addresses of the different positions, and also the addresses in the memory of the computer. And this will cause more problems and more difficulties. Yeah, you need a lot of sorting algorithms to speed up the simulation. And of course you can imagine here At this fixed mesh, you will not change the amount of cells during the simulation run. It always stays the same. But here at this particle simulation, what happens if one droplet is divided in two droplets, or if one droplet is burned and disappears, then you have to change all the addresses in the memory during the simulation. You have to allocate again memory during the simulation. This is not really good for a timer.